In the last video, we looked at standing waves created by sound waves in air columns or tubes. Standing waves are produced when two waves of the same frequency are moving in opposite directions and interfering with each other. But what happens if the waves had different frequencies? Consider the following case where we have two sound waves that have slightly different frequencies. The superposition of the two waves produces a complicated interference pattern, where some parts of the waves interfere constructively when they are in phase with each other, and other parts interfere destructively when they are out of phase with each other. If wave 1 has an amplitude A1, a wave number K1, and angular frequency omega1, while wave 2 has an amplitude A2, a wave number K2, and angular frequency omega2, then it can be shown, but not here, that the sum of the two waves is given by a product of a cosine with a sine function. The sine part of the resultant wave causes a medium to oscillate at a frequency that is equal to half of the sum of the two frequencies. This is the frequency of the sound that is perceived by the listener. The listener also hears a lower frequency, known as the beat frequency, which is equal to the difference between the two wave frequencies. The straight line in the beat frequency equation means absolute terms and removes a negative sign in any result. The beat frequency is a consequence of the cosine part of the wave function, which creates an envelope that restricts the amplitude of the wave as shown in the orange curve. The result is a wave consisting of periodic variations in the wave amplitude. We perceive these variations as periodic changes in the sound volume, which we call beats. One of the applications of using beat frequencies is in the tuning of musical instruments. Take for example a guitar string that needs to be tuned. In order to tune it, we first need to know what frequency of the note it is. We can do this by comparing the sound wave of the guitar string with that of a known frequency, for example from a tuning fork. Let's take the following situation, where we use a tuning fork with a frequency of 350 Hz. When we mix that sound with the sound from the string, we hear 30 beats in 5 seconds. So what is the frequency of the guitar? 30 beats in 5 seconds gives us a beat frequency of 6 Hz. If we use the beat frequency equation and let F1 be the frequency of the tuning fork and F2 be the frequency of the string, then F2 is equal to 344 Hz. But we could equally let F1 be the string frequency and F2 be the tuning fork frequency, which gives us F1 being 356 Hz. To know which one is the true frequency, we would need to calibrate it with a second tuning fork. So a second tuning fork with a frequency of 360 Hz is used, and we now hear 20 beats in 5 seconds. So what are the two possible frequencies? 20 beats in 5 seconds produces a beat frequency of 4 Hz. Again, the two possibilities when used with a 360 Hz tuning fork are 356 Hz or 364 Hz. Given that 356 Hz is valid for both tuning forks, then the frequency of the guitar string must be 356 Hz. In summary, when two waves of slightly different frequencies superpose or interfere, the resultant wave has a frequency that is equal to half of the sum of the two frequencies of the waves. The resultant wave also has a beat frequency given by the absolute difference between the two frequencies.